quantum gravity in 4 dimensions is usually said to require strings or require some other extra structure. You have some new interesting results, which we're premiering today.
Okay. So I used to believe it, that quantizing gravity was this, required this huge amount of extra paraphernalia, extra dimensions, strings, membranes. The whole story has become more and more complex as time progressed without actually solving any real problem. And what I mean by real problem is what happened at the Big Bang, what goes on in black holes, is there information loss? These kind of questions have not been solved by these very complex frameworks for quantum gravity. So what we've recently realized is that there's rather a simple-minded approach to quantum gravity, which actually has been around since the 1970s, was begun by somebody called Kelly Stell, who unfortunately passed away recently. But he wrote a paper arguing that if you include terms in the gravitational action, so you generalize Einstein's action. Einstein's action involves the curvature of space-time and also a length scale, which is called a Planck mass or Planck length or Newton's constant. It's all the same thing. So there's a scale in Einstein's theory of gravity. If you include terms in the action which are the square of the curvature,
in addition to the
regular Einstein action and the cosmological constant, which is has no derivatives, then you have Einstein's term, which has 2 derivatives because it's a curvature, and then you can include curvature squared terms, and that makes gravity much more like a gauge theory, because in a gauge theory, the action is an integral of the curvature, the field strength squared. Maxwell's theory, QCD, they all work the same way. So in gravity, you can put the curvature squared into the action. And then there's almost a trivial argument that tells you that that theory, which includes Einstein, but also these 4 derivative terms, is renormalizable. Now, renormalizable means that when you do quantum field theory and you calculate things, it is possible to, although you get infinities in various calculations, you can absorb these into redefinitions of the coupling constants. And so basically you're led to a sensible theory with what we call a continuum limit. Namely, at short distances, the theory is completely under control. So there is a renormalizable theory of quantum gravity, which has been known since the 1970s. And as I say, this is the simple-minded approach. Now, there are reasons why people have more or less abandoned it, though they keep coming back to it. It's called quadratic gravity because it's quadratic in the curvature. The action is quadratic in the curvature. So, there's actually more and more interest in this possibility, which certainly is the simplest possible theory of quantum gravity. So it's renormalizable, and then in the 1980s, Avramidi and Barvinsky showed it's asymptotically free. So just like QCD, the theory of the strong interactions, when you go to short distances, the coupling constant goes to 0. And it becomes a trivial theory of just waves which don't interact. So you can imagine at very short distances, this theory is really extremely simple. So what's wrong with the theory? All those statements I made about renormalizability, asymptotic freedom, they are the Euclidean theory. That is how we do computations of the strong interactions, QCD. You can put it on a lattice and study, the theory, but the only way we know how to study non-perturbative properties of any field theory is to work in imaginary time. Okay, the reason is that if you work in real time, then the quantum mechanical path integral is very oscillatory. It involves the imaginary number, exponential imaginary number. It's oscillating like crazy, and if you try to integrate anything, these oscillations are just impossible to control. if you do it directly. So you have to do some trick to control those oscillations. And going to imaginary time is a beautiful mathematical trick which converts an oscillatory integral into a perfectly damped convergent integral. So there's this mathematical trick which people have used forever in quantum field theory and in QCD, but not much in gravity. It doesn't work with Einstein's theory of gravity. People have studied that. But if you include these squared curvature terms, they suppress the curvature on short distances. And it looks like this theory is sensible in Euclidean time.
I subscribe to The Economist. Their science and their AI coverage is among the best I've found anywhere. And I say that as someone who reads plenty of it. I'll give you some examples. They just ran an analysis on how attitudes towards science are changing in American politics and what this means for research and funding in scientific institutions moving forward. This sort of high-quality reporting is fantastic. They even covered how dark energy may be weakening over time. Now, if that holds up, it completely changes our understanding of the universe's fate. If you watch this channel, those are exactly the kinds of questions that we explore every week. I subscribe to The Economist because their science and their AI reporting regularly surprises me with how deep it goes. And they're also, of course, known for global affairs, both political and economic reporting. They are top tier, and interestingly and flatteringly, TOE is one of the only podcasts that The Economist partners with. So as a listener, you get an exclusive 35% off. That's not a deal that they have just anywhere. Head to economist.com/TOE to subscribe. That's economist.com/TOE for 35% off.
So now that's all very well. What I'm saying is that it looks like there's a sensible theory in imaginary time. But we don't live in imaginary time, we live in real time. So we have to do this procedure called the Wick rotation or analytic continuation from this imaginary time to real time. When you do that, there are two disasters strike, and this is why people sort of abandon this approach, although they keep coming back to it. What we've done recently is half understand how to deal with that. Okay, so the two problems, one of them is probably the oldest no-go theorem in physics. It's called the Ostrogradsky theorem. And so in 1850, Ostrogradsky, I think he was in St. Petersburg, decided to generalize what Hamilton had done with Hamiltonian treatment of classical mechanics. And so Ostrogradsky asked, what if instead of F equals ma, instead of a second derivative equation, what if we had three derivatives in the equation of motion, or four or five, or any number of derivatives? Does anything go wrong? And he found something very interesting, which is the Hamiltonian, or the energy of the system. If the equations of motion have more than two derivatives, then the energy, or Hamiltonian, is what we call unbounded below. You can have configurations of arbitrarily negative energy in this higher derivative system. Now that, on the face of it, looks like a disaster, because if you brought such a system into contact with the real world, where generally the energy is positive, this system could interact with everything else, and its energy could go down, and the energy of everything else would go up. So it's an infinite source of energy. And we don't see such things in nature. And they might be wildly unstable. So this is called the Ostrogradsky instability. And in general, it's true. If you tried to write down a high derivative system, you will find it's unstable. In general, there are exceptions, but in general, that's a problem. So people got very worried about this, and often when people were building quantum field theories, and actually the first person, as far as I know, the first person to try to use a higher derivative quantum field theory was Homi Bhabha, who's an Indian nuclear physicist. And people were trying to understand nuclear forces, so they're trying all kinds of models and field theories. And Bhabha and Heisenberg and many other field theorists played with high derivative theories. The reason they played with them is they thought it would make quantum field theory more convergent. it would reduce the infinities. And it's related to the fact that gravity with 4 derivatives is renormalizable. So it's a similar reason. Now, the disaster that happens in the quantum theory is slightly different than the classical. What you find is that the space of quantum states does not have a positive inner product. It has what we call negative inner product. And states of negative norm are called ghosts, traditionally in physics. What people have often said, and what we realized is wrong, is that a state with negative norm corresponds to a negative probability. Okay, and you'll find this argument everywhere in the or many places in the literature that whoops, we can't allow negative norms; they're unphysical. They correspond to negative probabilities. That's just not true, because a quantum state is nothing but a label for a system. Its norm is neither here nor there. You can't observe the norm of a quantum state. Okay, so you've got these labels. Some of your vectors in this abstract space of state have positive length squared, let's say, and some have negative. So it's like in Minkowski space-time. We have distances which are space-like or time-like, and one of them is negative and the other is positive. And some are null. There's some null directions. So then the question we wanted to address is, can you live with a quantum theory in a space of states which has these 3 possibilities: positive, null, negative norm states? And what we found is, so mathematicians were studying this, and this is called a Krein space. It's a generalization of Hilbert space. And what we found is that provided there is a certain discrete symmetry in your theory, which we call ghost parity symmetry, and it's a very trivial thing. It's an operator which, when you act on a negative norm state, gives you -1, and acting on a positive norm state gives you +1. If you have a theory where that operator is a symmetry of the theory, you can now define transition probabilities without ever normalizing the state. And the way you do it is with projection operators. Okay, so even if I'm in Minkowski space, it's a non-degenerate. Every vector can be uniquely expressed as a linear combination of, let's say, space-like and time-like vectors. There's nothing singular about it. And the way you project, you can still project a vector onto its components, space-like or time-like. So you can do the same thing in this Hilbert space. But what you have to do is replace the Born rule. In quantum mechanics, the probability for an event is the inner product between an initial state and a final state squared. Okay, and now, if you were going to normalize this, so normally we think of those states as being normalized. Integral of wave function squared is 1. But imagine you can't normalize now because you're in this more general space. So what you do is you replace the Born formula, I, then some kind of matrix transitioning you from I to F. This is some time evolution operator. So IF, IS, that's called the S matrix, ISF squared would be the normal procedure. So let's replace the initial state. So we've got 2 copies of the initial state because we have this thing squared. Replace the I with dividing by its norm. Now you have a projection operator. So a completely equivalent formulation of the Born rule is to say, project onto initial state, evolve with the S matrix, project onto the final state, evolve with the S dagger complex conjugate, and trace the answer. Trace means sum over all states. That'll give exactly the same answers in normal quantum mechanics. But the beauty is, because now it involves projection operators, it gives sensible answers even in a Krein space. And what we've shown is that provided the S matrix or Hamiltonian of this theory has this symmetry, the one I mentioned, the answers you get are always positive, and the probabilities always add up to 1. So we found that in dealing with theories like which have 4 derivatives, we have to very slightly generalize the framework of quantum mechanics, but essentially it's a trivial change. And then we find all the probabilities are positive. So even though there are ghost states, you still trace over them. You trace over everything. So this is very exciting because now I have to say that there's a caveat, which is that we haven't solved quantum gravity yet, but we're halfway there. That's optimistic, of course, but that's a nice way of saying it. So when you look at this quadratic gravity action, there are 2 terms which are allowed. That's all. The symmetries of general relativity only allow 2 terms. One is what's called the Ricci scalar squared, and the other one is the Weyl curvature squared. And this is the most general action. So there are 2 couplings you can play with. What we've shown is that if you take a limit where one of those couplings is 0, that basically decouples the graviton and everything associated with the Weyl curvature. You just decouple. You're left with the curvature scalar. That action is renormalizable, asymptotically free, and gives positive probabilities. So we claim we understand quantum gravity in a certain limit, in which the only degrees of freedom are over the local scale of the metric. So this is fine for describing cosmology. Even there are black hole-like solutions to this theory. It's a kind of toy model for quantum gravity. The trick we used to make sense of it may or may not apply to the full thing. We will have to search in the full theory, is there a similar discrete symmetry, this thing that gives +1 on positive norm -1? If there is, then this will be a complete theory of quantum gravity.
Okay, what are the assumptions that go into this theory?
Well, let me first say what the assumptions were behind the claim that you need strings and 10 dimensions to do quantum gravity. The assumptions underlying that claim were that essentially the only allowed theories had 2 derivatives in the action. Okay, so when people quantize strings, they were not considering theories even of strings which had 4 derivatives. Okay, so that was one assumption. There are plenty of other assumptions. Probably the strongest assumption was that you have to construct the theory only in perturbation theory. Okay, so the thing that's always bothered me about string theory is it has no full formulation. There's nothing like general relativity where there's a principle that gives you the full nonlinear theory. String theory is kind of constructed with trying to respect certain principles, like Lorentz invariance and the unitarity, positive probabilities, and so on. But string theories, the assumptions were really rigid. And one of them is that the theory lives in a Hilbert space, which means that the norms of all quantum states are positive. And now that we've seen that you don't need that assumption, the whole thing has no basis. I mean, if it's true, we think it's true, we have an example of a theory which doesn't require that assumption and which is what we call UV complete. It has a full continuum formulation. This is a self-contained complete theory, like QCD, we believe is such a theory. And yet it doesn't live in a Hilbert space. It lives in a space with more like Minkowski space, with positive norm states and negative norm states and null states. So just a tiny generalization of the orthodox principles means you don't need strings, you don't need extra dimensions to describe gravity. So that's quite shocking. And of course, it begs the question, what are the other assumptions that people were making which led them to conclude there's a multiverse? You make one false move in theoretical physics and you're totally wrong. Okay, so that's the danger we all have to worry about. And I think people are not sufficiently worried about that. We should be examining very, very closely each one of our assumptions to say, is it really necessary? Or is it just that we're traditionally used to making that assumption?